Hey, this is Josh, and this is going to be part one of a two-part series of the week 4 of the Plutus Pioneer program. Week 4 is extremely long, spanning roughly 2 hours, and the first 1.5 hours talks about a concept called monads and how they're used with these other types called maybe either and a custom type we implement ourselves called writer. I probably won't do this topic justice, so do refer to the lecture itself. I also include other resources in the description below to help you learn what monads are, but we'll do our best. So that being said, without any delay, let's get started. The first thing in lecture 4 was about side effects. Side effect is basically a method or function that changes the state of your code. For example, if we have a class called side effect and it has a private field called num, which is an integer, if we have this function setNum, which would set our field to be the number that we're given, which you can see over here, this would be a side effect because we are changing the state of this class. This poses a problem because we want to be able to rely on pure functions, which is a function that would always return the same thing no matter based off of the parameter you give it. So getNum, if this was a pure function, it would always return the same thing. However, because we have the setNum function, this value can always be different, and so this is not a pure function. An example of a pure function is we have this method called multiply by 2. We're given an integer n, and then the return value will always be the same if we give it the same n. If we give it 2, for example, 2 times 2 will be 4, and it'll always return 4. And this is the Haskell equivalent. We have a function multiplied by 2. We're given an integer, and it returns an integer. And we call our integer a, and then we just multiply a by 2. And just like in the Java example, no matter what a we give it, we'll always multiply by 2 and return it, and that would be the same value. Now, why go through all the trouble? Well, the Cardano team wanted to avoid developers writing code that has state, such as we see over here, because that's prone to making errors in your smart contract. And we can do that by using functional programming that enforces writing code that has no side effects, so that developers can write bug-free code. Now, unfortunately, what I said was not completely true. Otherwise, we'll have problems with receiving inputs from users. To rectify this, Haskell has something called I/O, which allows the Haskell program to receive input from the user, whether that's in form of text files or string inputs. An example of that that was mentioned in the lecture was there's a function foo that takes in a type IO that is of type int. Specifically, that means the code takes in some value that is a integer. Now in the lecture, there were some examples that we went through. For example, put stringline is actually a function that takes in a string and then prints that string onto the console. There were many more examples in the lecture, so I highly recommend just following it. I'm just giving a very high-level overview of what I/O is. But on to the next topic. Now, what is an I/O actually? Now, before you read the screen and become overburdened, I'll just quickly guide through this. If you do a :I at an I/O to get the information about it, you'll see that I/O is actually a new type, and it has multiple instances. Specifically, it can be something called an applicative I/O, a functor I/O, a monad I/O, and so on and so forth. Monad is actually important for smart contract, but we'll talk about that later. If we were to look into some of these implementation of these types, for example, functor, you can see right here we do a :I functor. You see that a functor can have multiple instances too. It has something called a either or a maybe. Now, we'll talk more about this later, but these are important for smart contracts because they'll be using these properties. Now, we'll go talk more about these instances later. However, on the very high level, to at least wrap your mind around it, I like to think of these as abstract classes in a Java equivalent. They provide basic functionality that you need to define yourself. So the first thing we're going to talk about is what the maybe type is. So maybe is the type, and what it returns is it returns another type called nothing or just. You can kind of think of this as an optional parameter in Java. For example, it can be like an optional integer. It could return 3, for example. And the other possibility is that there is no integer and it's actually just a null value, which in this case would be nothing. Maybe it's just a type that has two possibilities. It can return whatever value that it's storing, or it can just return nothing. An example that the lecture went through using this is we have this function called foo, and it takes in 3 strings, which we call xyz, and then it returns a parameter called maybe int, which is basically a optional value that returns an integer. And so we read this code, and what this code is saying is that there's a function that we import from Haskell called readMaybe, and we give it our first string x. So what readMaybe does is it takes the string, it parses it to see if it's a integer, and if it is, it just returns that value, which we call k. Otherwise, it just returns nothing. And so what we're doing is we're doing a case of this, meaning that we get this maybe value back, and if that maybe that we get is actually a nothing, we return nothing. And if it's not nothing and it's just a k value, or whatever the integer form of x is, we can say that's 1 if we look at this example. Then we run our next case statement, which we call readMaybe of y, which is the exact same thing. If y is actually an integer, then we just define it as L. Otherwise, if it's nothing, we also return nothing, which would cause the whole code to stop executing. And so on and so forth. We do the same thing with z, and if it's nothing, we just stop this whole entire code. And at the very end of all this code, we return the value just, which at the end is still just a maybe. Like nothing and just are both maybes. And we would create the type just, and we would concatenate our values k, l, and m together and return that. And that's all a maybe is. It could either be an actual value, or it can just be nothing or null. So an example use case of this function is right here. If we call foo, we pass in the 3 strings, which is 1, 2, and 3. Note that all 3 of them are strings and that we're concatenating it. And then I didn't include the return value here, which I should have, but it would return the value just 6. Now, if we were to give it letters or an empty parentheses, one of these case statements would return nothing, and that would pass nothing back, and the return value of this whole entire operation would just be nothing. Later on in the lecture, it was described that all of these types that we talked about, maybe either in another one that we'll look at later called writer, has a superpower. And the superpower of maybe is basically throw an exception. And so that's the high level of the maybe type that we saw when we were looking at IO. But I promise you'll see why this is relevant later on, so just stick with me. Now, we can actually improve upon this and make this code simpler. Because notice how we're just repeating this case code multiple times over and over. We can do better by encapsulating this inside a function and then simplifying the call code, the foo function, by using that, the helper function that we create. So let's see how that works. All right, so stay with me. To help simplify the code, we have this new helper function called bindMaybe. It takes in 2 parameters. It takes in the maybe of type A. We don't know what A is, but we don't really care what A is actually in this instance. And then we take in this new syntax that we've never seen before, and it's basically an anonymous function. Anonymous functions are basically just functions that you define inside the code itself. It's very commonly used in JavaScript, and occasionally it's used in Java when you're overriding a function of a class. Instead of redefining the whole entire method signature, you can quickly write an inline function to save on time. I recommend just doing a quick lookup if you aren't aware of it, but in your mind, just think that this is a regular function that we pass in as a parameter. And this function that we pass in, it takes in a type A, and it returns another maybe, which is of type B, which is the type int. And then with these 2 parameters, we're going to return a maybe of type B, which is an integer. Now, I won't lie, this is more of a Haskell way of thinking, in my opinion. You wouldn't normally think of this in a object-oriented programming, so we're just going to take it as it is and just kind of read it and understand what's happening. We do something called pattern matching. If the first parameter we pass in, the maybe a, is of type nothing, we don't care about the anonymous function that was given to us, and we just return nothing. Notice if we look inside our previous code before, if the value that we read maybe of x, if that returns nothing, we just return nothing. And that's mirrored up here. Because essentially, maybe a is actually just us passing the maybe of the value x, which is our first parameter. The second part of is that our maybe a up here is not actually nothing. It's actually a value, which we'll call x. So we extract that out and we say, okay, just x. And then we call our anonymous function f. And because that function only takes in one parameter, which is a, we just call that function, and then we give it x, which is our integer value. Now, I know this sounds complicated, but we'll break it down a bit. I just want to point out that if our maybe a is actually a just value, like x, this is equivalent to us saying in our case statement down here that we have a value just k. And then we want to call the next step of our case statement, which is going to be represented as f, and we'll look at that later. Now, if we look back inside our foo function, we call the function byMaybe. And remember, this is just syntactic sugar what we have when we put the byMaybe in these apostrophes. What we're really calling is byMaybe, pass in the value maybe, remaybe x, and then pass in this syntax right here, which is the anonymous function. This is how Haskell defines it. And what this is saying is that we're creating an anonymous function k that takes in a type, one parameter, which is k. We define it as an integer up here. This k value is the parameter a inside our anonymous function that we pass in. So specifically, if you look in our byMaybe code, where we pass in x into our function f, the x value is the a that we see, which inside the foo function is represented as the variable k. In this example, if let's say x was 1, then the value of k would also be 1. And so how this reads is that, let's say we're given the value 1, 2, 3 for our x, y, z. What's happening is our first instance of byMaybe, we're going to give it the value of remaybe x, which is maybe a, so maybe 1. If 1 is nothing, which is impossible, we just return nothing and our whole code fails. However, if 1 is something, which is 1, we would just call our anonymous function that we give it, which is this whole k right here, this whole entire code right here. Well, we'll pass it x. X being this k value that we're setting. So specifically, k here in this instance would be 1. And so we have that 1, and then we trigger, and then now once we call the anonymous function, we trigger the code that's executing inside of it. In that code, in this anonymous function that we set right here, we call the function byMaybe again, and we pass it the value readmaybe 2. And remember, we say y is 2 and z is 3 and x is 1. So remaybe of y would just give us a type maybe 2. And then we'll pass in another anonymous function, which is this L right here. And this L would be this code down here. Oops. And once again, repeat that same pattern. So we have maybe 2, and 2 is not nothing, so we don't return it nothing. So we get the just value, so just 2. And then we have this L function, anonymous function that we passed in. So we continue this same pattern. We call the anonymous function f, and then we give it our x value, which in this instance is 2. And so L now is 2. This is 2, and k is 1. And then this code repeats the same exact thing again. And now it reads read maybe z, which is 3. And then it calls by maybe with maybe 3. And then it gives it another anonymous function, which you can see right here, which in this instance just returns a sum. And we don't want that again. So we go through the same logic again. So we received in our by maybe a maybe 3, and then we're receiving another anonymous function, which in this instance is just k plus l plus m. And once again, maybe 3 is not nothing, so we don't return nothing. It has a value 3. So we have this anonymous function called f, and so we just pass f our 3 value, which is represented by this m, so m is 3. And then finally, going through all of this, we can finally return this anonymous function, which all it does is it returns a just value of k plus l plus m, which then will give us 6, which if we recall which we can surmise from the original foo example that if our string value was 1, 2, and 3, at the very end, we would still return 6. Now, for those of you familiar with the concept of recursion, this might seem kind of familiar, and that'd be great. However, if not, I highly recommend just learning a bit more about recursion. Recursion is very common in Haskell, especially since there's no concepts of for loops. And so if you want to actually iterate through something, we have to use a function and kind of recursively call it over and over, just similar to what we're doing over here, to be able to iterate through a list, for example. So hopefully I made things clear a bit. I will admit that this does take some actual knowledge about recursion and anonymous function. Hopefully you might be able to gather some intuition about this now. Do pay attention to this method signature that we see right here. It's actually very important later on. But this is all the lecture talked about for maybe. So next we're going to talk about another type called either. Now, either is similar to maybe in the sense that there's 2 values. And as you can see right here, either allows you to define the 2 types. There's your left value, which in this instance, it's defined as a string type. And then you have the right value, which is defined as a integer. So we're going through the same exact example again. In the previous code, when we were using maybe, we just threw a nothing and we returned that, and then that would stop the whole entire function. However, we want to improve upon that with either. Instead of just failing outright, we want to actually return a error message first. And you can see that in this function called read either. It sets the a value to be of type read. We don't really need to worry about this, but it takes in one type, which is a string, and then it returns either type with the left value being a type string and the right being the type read. We do the exact same code that we did in the maybe. So we call our string s, and we do a case depending on the value of read maybe s, and where read maybe just parses the string that we give it into an integer, and it's a type maybe. It could if the operation fails, it returns a nothing, and if the operation succeeds, it returns a just. And so, just like before, if it was nothing, something more interesting happens. We return the left value, and that is a type string. What this $sign basically means is evaluate the function to the right first. And what all of this does is it concatenates the string that we written in it with the text can't parse. And so if the user enters something like peanuts, we would return the message can't parse peanuts. And that would be the return value for this either. On the other hand, if our string that we pass in is a valid number and we return, let's say 1, then we would return the right option of our either, which is just the a value itself. So that can be like 1 or something. And so that's what this helper function does. It's very similar to maybe, but instead of returning nothing, we would return a left value that is of type string. And so if we look inside the actual foo function again, it takes in 3 strings, very similar to the previous foo function, and all 3 strings could be parsed into an integer, and we call them x, y, z. We can just think of this as 1, 2, and 3. Going through the code quickly again, we call our new helper function read either, and then we pass it our first value x, which is 1. If 1 is invalid, then we would call the string that we got out error, and then we just return that, and then somewhere in the code we would just print that out. On the other hand, if we would return our right value, k, which is an integer, we would do the same thing over again and call the next case statement with our y value, which is 2. And this is exactly the same thing as our maybe, so I'm not going to go through this whole entire thing. But at the very end, with our z value, if we do get a right value, we just return our final either, which is our right, because remember left and right are both of type either. And then we would just return our right, and we just concatenate these values klm, which is 1 plus 2 plus 3, and that would give us 6. And a usage of this, as you can see in our code right here, is it's exactly the same. We still call foo, and then we give it 3 strings, 1, 2, and 3. The only difference is that if we do encounter an error, instead of printing out nothing in the statement, we would actually print out the actual string itself. And just like maybe, if we were to give the superpower a name of our either function, it is to provide a error message on failure or when you throw an exception. And just like the maybe, you notice that we are writing a lot of repeat code in all of our cases. We can simplify all of this by doing the exact same thing we did earlier and convert these into helper functions to generate this value. And so we'll just kind of quickly go over that. Just like in our maybe example, we create another helper function called bind either that will help us simplify our code. Bind either takes in 2 parameters. First, it takes in a either with the left type string and the right type being a. And in this instance, we don't care what a is. We just know it's some value. And then we take in an anonymous function, which takes in a value a, and it returns another either of type left type string and right type b, which is just another arbitrary type. And then the return result of all of this whole entire function is we return a either with left string and right b. Inside our definition, if our either that we pass in is a type left or an error, we just return the error message. If it's a right value, or in this instance is an integer, we would define our function. We will call that function with our x value. And so let's go through this example quickly again. So we have 1, 2, and 3 for our x, y, and z. We have this function called foo, which takes in 3 strings and returns a either. This is nothing different from what we've seen before. So the first thing the code does is it calls our helper function bind either, and then we call our read either helper function that we defined in the previous example, and we pass in 1. So remember, if the string we're giving is not a valid number, we would just print this message. Otherwise, it would return a type either. And so we pass that value, the either value, into our bind either function. If our read either returns a left value that was an error, we just return that error back out. And otherwise, in this example, it returned the value 1 because 1 is valid. And so we will call our anonymous function f, and then we'll pass an x. And so just to reiterate, this function that we pass in is this whole entire chunk of code right here. K, our value k, would be our x, which is really just our 1. And then we pass that into our anonymous function. And then inside our anonymous function, we would execute the same code. We would call bind either, and then we would pass it the read either of our value 2. And then we pass in our next anonymous function, which is this code right here. And we do the exact same And then we do the exact same logic. If we get an error because we got a string that's not a number, we just print out that message and then we terminate everything because we don't call the helper function that we passed in. However, if we do parse the integer correctly, we have right 2 in our function. And we just call our function and then we pass the number 2 into it. And that would be represented as our L. So this is 2. And then inside of that anonymous function, we execute another instance of bind either. We pass in our value 3, and we pass in our next anonymous function, which is this write KL plus M. Same logic, 3 is a valid number, so we don't return an error message. We get the write 3, and we have that anonymous function, so we just pass our value 3 into our anonymous function, so M is 3. And then inside this anonymous function, we just return the write value, and that write value is the concatenation of, or the addition of K, L, and M. So combined together, that will return the value 6 as our either over here. And then if we look at the compiler after we call foo, we would get the value write 6. And so that's just another simplification of that either example that we looked at. But once again, I do want to point out to pay attention to this method signature that we have. And so that's the example for either. We're going to look at one more example with another function called writer. So unlike the 2 other examples, writer is actually a custom data type that we create ourselves in this specific lecture. Writer takes in a type A, and A can be anything. It's a generic that we define. It can be an integer, it can be a string. But in our code example, it's going to be an integer and a list of string. Later on, you'll see it's just a list of error logs that we want to print out. And then there's this deriving show, and this is basically just a way for us to easily print the writer type on the console. They define a helper function called number. This is actually used in the actual foo function itself. It's just a helper function to generate a writer data type. It takes in an integer, and it just returns a writer of that type integer. And see, we call the integer n, and all of this function does is it creates a writer type, and it gives it the value, the integer value that you gave it, and it creates a list of string, and specifically that list only has one string, and it's just a concatenation of the words number colon with the integer that you gave it. And show just changes that integer into a string for you and then concatenates it together. And you can kind of see that down here, over here. And so that's just a helper function that generates it. An example usage is right here, and we call number 1. And so there's another helper function that was defined. It's called tell, and tell just takes in a list of strings, and it passes back a writer of unit type. And all this code does is it returns this writer, and because we never explicitly defined our list, it just implicitly implied that this final list is applied over here without us needing to actually write it out. So it's just some syntactic sugar. And so now onto the actual foo function itself. So foo, if you haven't seen this pattern before, is essentially it takes in 3 writers and it returns another writer. And so we call these writer KXS. K is the number and XS is our list of strings. And we just define all 3 of them. So the next syntax that we see right here is we have this thing called let. And in JavaScript, let is basically just how you define a variable type. And that's exactly the same thing here. All we're saying here is that we are defining 2 types, S and this writer. So S is just simply a addition of our 3 integer values. So if this was 1, this is 2, this is 3, S would be 6. And then we do pattern matching with our writer. We are creating a new writer. We don't care about what the integer is, but we do care about our list of strings. And to do that, we call our helper function that was defined called tell. And then we give it a list of string, which just basically gives us the sum. Now that we have these variables s and us defined, we use the in keyword to write the code that we want to return. And the code we want to return is we want to create a new writer. And this writer has the type s, which is the value 6. And this $sign mirror, once again, it's just means evaluate the following statement first. And that following statement is basically just concatenating these 4 lists that we defined together. And then we return that as a writer. And I believe the example is actually wrong because it's missing the sum 6. I might have pulled it out incorrectly, but the writer type we see has that sum 6. It has the concatenation of number 1, number 2, and number 3, and it's just missing sum 6. And I believe that's probably just because I grabbed this snapshot of this before the code was updated, so that's a mistake on my part. Now, if we were to give this a superpower, this would be the ability to log messages, because as you can see, we just kind of carry the messages that we passed in, and then we just concatenate everything together. And this will be handy when we look at smart contracts later. Now, just like before, it might not be obvious because we just kind of concatenate everything together, but we can actually simplify the code and just create a helper function that would handle all of this. So let's take a quick look at that. So we're back here again. We're going to create another helper function called bindWriter that will help us simplify the code. One thing I will mention ahead of time is that this technically doesn't actually produce the same result as the previous example. It still creates that sum, but it just returns a string of that sum, and it doesn't preserve the other 3 strings that you included initially. And so let's quickly take a look at this again. So our bindWriter function takes in 2 parameters, writer of type A, and that's just our integer in this instance. And then we pass in an anonymous function of type that takes in a type A, which is that integer, and it returns a writer of type B. And then this whole function would just return that writer of type B. And so we define our types like usual. Our writer has type A, which we just call the value A, and we get our string, our list of string, and we call that XS. And then finally, our anonymous function is just F. And then we do a similar code as we did earlier. We use let to define our variable. So we define a variable called writer, which has the integer type B, and it has the string YS. And we get that by calling our anonymous function, which will return this writer B value, which we're using right here. And then we just pass that our integer A. So either way, we call this anonymous function F, we pass it A, and that returns us our writer type B, which is over here. And so now that we have our writer B defined, all we do is return another writer with the type B that we received back, and we just concatenate our existing list of string from our first writer with the list of string from our second writer. And so let's go through our foo example again. Our method signature is exactly the same. X is 1, Y is 2, and Z is 3. So we call our bindWriter function. We give it our writer, which contains the value 1, and we give it this anonymous function. And so we look at this code again. Unlike before, where we actually do some evaluation, we actually just explicitly first call our function. Because we want to define what our writer of type BYS is, we just call our function F, and then we just give it the integer, which in this instance is 1. Our K is 1. And we do the same thing with Y. We pass in the value Y, and then we pass in the anonymous function with this L. And so if you look at the definition again, we immediately call our anonymous function first, F, and then we pass in our value Y, which is A, and that's 2. And so L over here is 2. And the exact same thing happens again. We call bindWriter, we give it our Z value, which is 3, and we give it this anonymous function, which is this whole entire block of code. In this third iteration, we call our anonymous function immediately, and then we just pass in our Z value, which is 3, and then we execute that anonymous function. And so inside this anonymous function, we first define our S value, which is K plus L plus M, so that's 6. And we're going to call bindWriter again one more time. I'm going to have to use a new color. And instead of passing in our sum like we did before, we're actually going to call our tell function, which, as you recall, ignores the integer and it just creates a list of string. Specifically in this instance, the string is sum of 6. And then we're going to pass in another anonymous function, which just returns a typewriter of the value S, which is 6, and an empty list. So let's evaluate this code again. We're going to immediately call our nonce function, and we're going to pass it a, which in this instance is just 0. And as you see in this instance right here, this 0 is over here is not even used. And what this function returns at the very end of our recursive call is a new type writer of type S, which is the sum up here, so that's 6, and we pass in an empty list. And so if you understand recursion, you think of this as our base case. We've recursed all the way until the end, and now we have to go bubble our code back up. So we're going back up from our previous nonce function to up here. And so we just exited our nonce function call right here. We actually return the writer. So this writer that we get back, writer bys, is actually b is this s value that we defined. So that's of type 6. And so at the very end of our code, inside our green, we actually have a writer of type 6 and the text sum 6. And so now that we have that value, we pass, let's go back to blue, we pass this and we go back up to our back up our recursive call to our previous recursive function. So originally we just finished this in, we return this value, and now we've popped out of that and we're back up here where we came from. Remember, we're kind of just moving back up this stack. And so we have our writer bys, which remember b is now 6 and our list of string is sum 6. So once again, we create our new writer, and our writer is still type b, so we always will propagate our b back up, so it'll always be 6. So in the final z example, we have 6. And then we just concatenate our two strings together. And so our string, remember, is just the value num6 or num of z, num3, because that's what we pass in. And so we now have the text string 6, gosh, if I can write, and num3. Maybe not in that order, but you get the idea. We're concatenating it together. Once we have this value, we just return that, and then we exit our anonymous function. We finish the z, and then we go up to y, go back up, and we repeat the same thing. We pass in our 6, sum 6, number 3. So we define that over here, and then we execute the in function, and we do the exact same thing. We give it the sum 6. We have the text in our list, sum 6. Okay, I can't write. Number 3, and then we just add our new value, number 2. And this is the xs, for example, that we pass in when we first called the bind writer function. And then we use purple for our last one. So we have finally had the result from calling our lanonce function. And now we're going to pass this one more time back up to our kanonce function. And I think at this point you see the pattern. Our writer over here will have the type 6 as our b once again. And ys will represent this huge string that we've concatenated. And so we add the list of string from our x writer again, and the end result of this would be 6, sum of 6, number 3, number 2, and number 1. And then we finally, after all of this, return that as the parameter in our foo function. And this would be exactly the same as the previous example. I understand this is quite messy. If you're not too familiar with recursion or the Haskell way of doing things, it might be hard to understand, and potentially I could have made this even worse. However, I hope going through this example, I've given you an intuition of how you might start understanding this code. The final part of this example that the lecture went through is we're going to talk about monads and how everything we did up till this point is relevant to monads, and in turn, how it might be relevant to smart contract. So what's a monad class? Well, you can think of monad as an abstract function similar to the functors and applicatives that we've seen earlier. Monads essentially have several abstract functions, so to speak. We have bind and return and fail, and quite frankly, I don't know what this is. And each of these symbols or keywords have their own parameters and return type you would expect to see. So monad of type M over here has a bind function that takes in two parameters, the M type you take in and an arbitrary A value, and a second parameter, a anonymous function that takes in a value A and then returns that same M type with a B type. And the return value is that MB. And if that looks familiar to you, it should, because that's what we've been talking about earlier in our simplified examples, and we'll look at that later. So an example of us using this is, for example, in our writer class, if we want to make it a monad, we just create an instance, and it would be a monad, specifically a monad instance with the M type, which is writer. And then we want to implement some of the functionalities. We would just use where, and then we just define the functionality, which is return and bind, and then we just provide the implementation. So that's how you make one. So let's quickly look back to our previous examples in the perspective of a monad. So here we are, specifically we're looking at the bind function for our monad, which is over here. You note that we have the specific param and return type, and it should look very similar to you, because if we recall in all of our simplified example, like bind writer, bind either, and bind maybe, they all have a very similar format. The first parameter for each of them, we take in the type, which is a writer, a either, or a maybe, and then we give it a function, an anonymous function, that takes in that same type A, and then returns the M type with a different value B. And then we just return that writer B. So just looking at that writer example, we could easily set our monads implementation to be a bind writer, bind either, or bind maybe, because it follows the definition of the bind keyword. What are the benefits of using the monad? And in the lecture, there were 3 benefits that was given. First, it's to give a name to a pattern. For example, we have that bind, or the return, or the fail. The second reason is that there's a shared API that we can always refer to for a specific functionality. For example, if we always wanted to have a bind function where we give a specific type, then we can always rely on that bind to give us that type of functionality. And finally, probably what is most important is that it allows us to share functions that explicitly requires a monad type or a monad instance, but they don't really necessarily care about the implementation of the monad itself. And so the best example for this is abstract class in Java. So for example, let's say we have a abstract class called car, and it has a function called getWheels. There are different types of cars. For example, there are buses, there are trucks, sedans, and so on and so forth. We can create a unique instance of a bus class, and it can implement its own getWheels function, but it's so much harder to ensure that everything remains consistent. Instead, what we could do is we can have our bus class inherit or extend from the car instance, and then it would get any shared functionality, and more importantly, it has to implement its abstract getWheels class. And so, for example, a bus can return something like, 16 for wheels. And maybe, a truck, we have a small truck, and that's like 4 wheels. Similar to the idea of a monad, we can write helper functions that take in this car abstract class, because this is the base class of our bus and truck. And so we can do some operation, maybe get the wheels, and then based off the wheels, apply some logic. And that function that we write that takes in the car doesn't really care if it's a bus or a truck. It just cares that when it calls the getWheel function, it would get an integer back. And so that's the exact same thing with monads. We can create multiple helper functions that takes a monad, which can be anything. Remember, it can be a maybe, it can be an either, it can be a writer, and it would just apply some logic based off of what you give it, and then you would easily create functions that would be applied to multiple monad types inside Haskell, which is very powerful. So now let's see the practical example that was went through in this lecture. After going through all of our definitions on monad, we finally write a helper function in lecture 4. We take the next level and abstract away our implementation of foo itself. So here's the monad example again with our bind function and its definition for our convenience. And here's our foo function that we had earlier. And recall that foo takes in 3 strings and it returns a monad back, which in this case it's maybe. We're going to use the maybe as an example. And the string values are x, y, and z. And normally we would actually we would have our implementation detail where we would check the values of x, and if this is maybe, if the value of x is nothing, we just terminate and stop. Otherwise, we continue on and check the value of y. However, instead of doing that, we can call a helper function that was written called 3int. And 3int, if we look up here, is a function that takes in a monad of type m. So m is the monad type, and each of those monads has a integer as a value that it was given, and it returns monad of type int back. And for each of these parameters that we take in, we call it mx, my, and mz. We can just think of this as 1, 2, and 3. And then in this code, it does something very similar to what we've seen in our bind writer function. It uses the monad that we give and call it the bind function, and then we pass in our anonymous function, which is this over here. You can think of this essentially as we're calling bind, and this first is in front, and bind receives this ma and this anonymous function, and then it returns mb, which would be the end result, and inside our anonymous function, our k would be the a value that we've stored inside our mx. In this example, that would just be our 1 value, our integer 1. This is very powerful right here. Essentially, what we're doing now is we write this helper function called 3int that takes in a monad class, and it would, regardless of what our monad is, it could be a maybe, it could be a either, or it could be a writer. It would call the bind implementation that we provided for that specific implementation in our abstract class. Remember, think of the car example. Monad is the car. It has a abstract get wheel function. So it's just calling that get wheel function. It doesn't care what the implementation does. It just expects that the implementation does the correct thing. In this example, our monad maybe, we will call the bind function, which you can think of our bind maybe that we talked about earlier. And that bind maybe is the implementation detail of this whole function, and it will do whatever we implemented. Because maybe is a type that Haskell already provides us, that definition is already obscured away from us, but it's exactly what we implemented throughout this whole entire example. And the great thing about this is because we take in this generic monad type, this same code works for our maybe, it works for our either, and it works for our writer. Now we quickly go back a bit to our writer, which is over here. Writer is a type that we implement ourselves. So when we made it an instance of monad, our implementation essentially is that bind writer function that we wrote earlier. And so whenever we have a writer and then it calls the bind function, it would automatically, under the hood, execute the function that we wrote. And so the benefit of this is that you can create any helper function like we did over here with the bind maybe, with the 3ints. And we can just give it a monad, and we don't care what the actual monad type is, and we can just use the functions that the monad definition provides, and we can expect the correct results to occur. So I know the video was confusing. It took me a while to actually understand this, and hopefully this breaks it down and makes it more clear to you what's happening in this lecture. All right, so hopefully at this point you now have a stronger understanding of monads and maybe either in writer types that we've talked about in lecture 4. Now, the big question you might have is, Josh, this is great. I'm learning a lot about Haskell, but what's the point of all of this? How is this relevant to Plutus and smart contracts? Well, this will be the topic of the next video, which is part 2 of week 4, because I physically cannot keep up with learning about Plutus and my day job, and something had to give, and unfortunately, it's not my day job. But if you found these videos helpful, I definitely will continue along, probably just at a slower pace. Hopefully I won't lag too far behind. But stay tuned. I intend to do a fast follow, or at least as fast as I can, to talk about the rest of the videos. But a quick hint, monads, ethers, and maybes are used in smart contracts and in their code implementation, so it's not a surprise that we're talking about this. So it's been a long day. I'm going to sleep. I hope this video has been helpful, and stay tuned for part 2 of this video coming up hopefully within sometime this week.